Hi everyone. In this video, I'm going to discuss Lagrange multipliers, and we'll prove this in the case of 2D just as a review. If you're interested in seeing this proof in n dimensions, I would check out Advanced Calculus of Several Variables by C.H. Edwards. I think it's a good proof, but I'll just prove the 2D case because it gets significantly more involved in n dimensions. But this gives you the same basic intuition for the n-dimensional result. So basically the setup with Lagrange multipliers, if you haven't seen this before, so likely be a review. You've probably seen this in Calculus 3 at some point, but probably didn't prove it. So so you have a constraint function here, a constraint set. So here it's just a circle, and you have some constraint function g of xy minus r squared in this case equals 0 if and only if xy is in your constraint set S. So, and then these are level curves that I've drawn here. So you can think of whichever convention you want. We don't care about max or min here, but for the sake of usual color patterns, let's have darker be greater, so we're looking for a maximum here. The main idea here is that if I ask you, is this point a minimum or a maximum or minimum, you look at the level curve and you see that the level curve is not tangent to the surface. And if it's not tangent to the surface, that basically tells you that it's not a minimum. Why? Well, because you can see visually here that what I could do is shrink this level curve. I have some space to descend and still hit the constraint curve. And so I shrink and shrink and shrink until eventually I hit a point where I'm tangent here. And then if I continue this shrinking process, I no longer hit the constraint curve. So the maximum here must occur whenever this is tangent. Okay, so the level curve is tangent to S, and that is satisfied whenever the gradient of F is parallel to the gradient of G, where G is the constraint curve, and this is the function we're extremizing. Okay, and so here at the bottom, so this is a bit oversimplified where these contours are elliptical. So let's take the same elliptical contours, but let's put it on a more complicated surface. And let's look at this analogous point here. Again here, I've tried to draw this so that it's not perfectly orthogonal, but it kind of looks orthogonal at this point. So if I look now at the gradient of this, or the level curve, right? So the level curve here locally looks like that line. The point is that the function is constant along that line, and the function itself will increase fastest along the gradient. And so here, the gradient, I'm gonna draw this inaccurately because it looks like I did this orthogonal. But the point is then that the gradient points now, there's a component of the gradient that moves along the curve locally, and so we can increase the function along the curve. And this is how I view it intuitively. There might be better interpretations out on the internet or certain books, but I think this hopefully motivates a little bit of the intuition behind Lagrange multipliers. So let's go ahead and prove this in 2D, and again, I don't want to belabor it with n dimensions. But the main lemma that you use in this proof is if you're given the set S, which is the kernel of some function g, where g is C1, and you take P in the set where the gradient is non-zero, then there's some domain Q, a two-dimensional domain Q, centered at P, where you can get a differentiable curve phi that parameterizes the set S along here. So phi of 0 is P, phi prime of 0 is, this becomes important later, and where whenever you give me a point inside this rectangle that also coincides with the set of interest S, then this is contained in the image of phi. So basically that tells you phi parameterizes this curve. The idea here is that if you give me t and y, I know that g of t and y is equal to 0 because it's in the kernel. So ty is in q intersect s. I can invert this locally as a function. Let's call it y of t. As a function of t. And that well, let's even call this phi of t. Or no. Yeah, let's call it y of t. You can invert it locally as a function of t. This is the implicit function theorem. It's a famous result. If you haven't seen that before, just look that up. And that takes a while to prove. That's why I don't want to belabor this. So you apply the implicit function theorem, and that gives you your phi of t. That's the important part. So basically all it is you can think about it if you don't want to get into technical details at all. It's basically just saying these are the conditions you need in order for a well-defined map around P to exist. And then manipulating that map is the key part of this proof. So let's go ahead and prove this. So this is the statement. F is the function we're extremizing. G is our constraint function. They're both C1 smooth. F attains an extremum on the zero set S at a point where the gradient of P is non-zero. That means that the gradient of F at P is parallel to the gradient at G of P for some lambda. That is the statement. So phi is now a map from R to R2 as in the lemma. So this is phi of 0 is the point P of interest, and its derivative at 0 is non-zero. So we know G of phi of t is 0 for t small, because again, we only have this locally. Yeah, so for t small, we have this. So ddt of g of phi of t, which is phi prime of t dotted into the gradient. Oh, sorry. Yeah, let's not do that. This is equal to 0, which is equal to g prime of t dotted into the phi prime of t dotted into the gradient of g of phi of t. Go on to another page. That tells us that g prime of 0, in particular, dotted into g of phi prime of t, sorry. Phi prime of 0 dotted into the gradient of g of p, because remember phi of 0 equals p. That is equal to 0. Also, consider h of t is f of phi of t. Okay, so this h of t is basically saying, well, I have this parameterization phi of t of the curve, so I can actually say, well, let's look at this one-dimensional function, right? So now I can just view f like it's a one-dimensional function that does something like this, right? Where as a function of t, I simply get the value of my function f, and so we can take derivatives of this. H of 0 is f of p, so h attains an extremum at t equals 0. That tells us that h prime of 0 is 0, and h prime of 0 in particular is going to be, so again, just the chain rule, it's phi prime of 0 dotted with the gradient of f of p is 0. So this tells us that, okay, so basically gradient of g of p is orthogonal to phi prime of 0. And the gradient of f of p is orthogonal to phi prime of 0. And phi prime of 0 is non-zero. That's important, right? Because if phi prime of 0 is 0, well, of course, this trivially, that's the dot product. But since it's non-zero, that's the key punchline. That tells us that the gradient of g of p is collinear with the gradient of f of p. So there is some lambda with the gradient of f of p is lambda times the gradient of g of p. And that's the proof in R2. So the only thing I'll end this video with is, when you're looking in n dimensions, that proof is more intricate, A, because the mapping of phi is harder to, it's just more complicated, and B, this argument here, this becomes more complicated in n dimensions. Because let's look at 3 dimensions, right? If I give you that two vectors are, so just consider phi prime, phi prime of 0 is E1, gradient of g of p is E2, gradient of f of p is E3. They're not collinear, right? Because now you have an extra dimension where they're both orthogonal to phi prime of 0, but they're not